Hi, we're going to talk about the first lecture, Lecture 1. This is just kind of an overview, talk about what statistics is for a few minutes, and then give you some words, some vocabulary, and a few ideas that are needed just to start. Let me start out by saying that watching this video is not a substitute for reading the book and notes. It's more like a supplement. There will sometimes, often, be material in the book and notes that I do not go over or do not go over in detail that you will need to know. Okay, what is statistics about? You've seen a few things, no doubt. The mean and median, for example, are in the high school curriculum in Virginia and probably most places, and a few other little things. And that is part of it. In general, it's about describing data and about drawing conclusions from it. Those are kind of the two basic things in statistics. Describing data means things like putting into tables, making graphs or charts from it, and computing summary statistics like the mean or median or standard deviation. Various ways to describe a data set. To draw conclusions from data, well, we'll say more about that in just a few minutes when I say something about inferential statistics. But those are the two kinds, kind of the two big areas of statistics. The usual situation when statistics might be useful is that you have a very large population, or a population in general that you just can't get all of. A kind of standard example is suppose you wanted to know the average height of an adult American male. How could you possibly get at all adult American males to measure them? Right? There are over 100 million of them. They move around all the time. The set changes every few seconds as someone ages in or dies out. And there are adult American males scattered all over the world, sleeping under bridges in China and climbing up Ayers Rock or whatever. There's no way you can get hold of them all. So what you have to do is you have to pick a sample, which if you had some sense, you would pick in a kind of random way in hope that your sample would be representative of the population. And then you would make a calculation. You would take the average height of the sample, the men in the sample, and you would say, well, that's my estimate for the average for the whole population. Later on, you might want to know, or someone might ask you, well, how likely is it, for example, what's the probability that your estimate is within 1 inch of the true average height? And we'll see some calculations related to that later on. That's part of inferential statistics. Okay. I need to say this early on, you actually need much more than just things like an estimate of the mean in many situations. So for example, suppose you wanted to know whether a baby who was just born was seriously underweight. And you knew that the average weight at birth was 7.5 pounds. Well, that just doesn't tell you much. Right? Let's draw a number line here, right? And we'll put 7.5 right there. Right? Now the question is, let's say the baby who was just born was 6.5 pounds. Now the question is, how far away is that really from average? Right? Is it, if you knew that 99% of all babies born had birth weights greater than 6.5, you would think, okay, this baby is dramatically underweight, something seriously wrong. But if you knew that that number was really only, say, 60%, you'd think, oh, well, 6.5 pounds is pretty close to average, actually. Lots of babies are born in that range. And so you really need to know the distribution of the data. You need to know how the numbers are spaced out on the number line. Okay. Here's the first set of words. Usually you have a big set, as I said, called the population. Right? This is the big set. In theory, the population could be the same as the sample, but it usually isn't. Right? This is, in fact, you might say the entire set of individuals of interest. Right? If you're interested in the average height of adult American males, then adult American males, all adult American males would be your population. From the population, you choose a sample, right? And a sample is just a subset of the population. Right? That is, some of them. As I said, in theory, a sample could be the same as the population, but in fact, it almost never is. Okay, so in our example, the population is all adult American males. The sample is the 1,000, let's say, that we picked to measure. Right? There would be a variable of interest. The variable of interest here is the height. Right? In other situations, it could be anything, any single characteristic that you're going to measure or observe about members of your sample. Right? I won't write down a definition for that. Once you've got yourself a sample and you've started to measure or observe them, you're going to write down something about each individual in the sample. Right? You're going to measure a man, you're going to measure the height of a man, and you're going to write down that height. You're going to measure the height of another one and write that down, and so on. What you write down is called your data. Right? The data is the actual observed values, however you go about observing them. Right? They can just be observed, like watching people walk by in the street, or they can be measured or counted or whatever. Right? Just whatever it is, you write down various values of your variable that you write down to work on. Okay, once you have your sample data, you've measured the height of everybody in your sample or observed the eye color or whatever, then you probably want to do some calculation on it. Right? What you would like to do is you would like to have what's called the population parameter. Right? This is a value computed from population data. In our example here, ongoing example, that would be the actual average height of all adult American males. Right? Something we can't get at. What we have instead is the number from the sample, right? And that's called a statistic. That's a value computed from sample data. Can't seem to write here. Right? A statistic is a value computed from sample data in the same way that you would compute a value from the population data if you could get it. Right? And then your statistic that you actually can compute is an estimate for your parameter, which you cannot compute. All right, let's do a couple of simple exercises on distinguishing these two. Here we go. Jake measured the diameters of 100 ball bearings chosen from a shipment of 10,000. The average diameter was 1.1 millimeter. All right, we're supposed to distinguish all 6 of these in this situation, this scenario here. Okay. First of all, let's do sample first. That's usually easiest. What's Jake's sample? Jake's sample are the 100 ball bearings that he chose. So I'm just going to write that, the 100 ball bearings. Okay. He chose them out of a population. The population he chose them from was this shipment of 10,000. So I'm going to say the 10,000 bearings. The whole population here. What's the variable of interest? Well, what he wants to know, what he's going to be measuring, is diameter. So the variable here is diameter. Right? That's the characteristic of these ball bearings that he cares about. What's his data? Well, it's not mentioned here, and certainly there's no list of data, but the data will be the measured diameters. Right? That's what he's going to actually write down. What's the statistic? The statistic is a value computed from a sample. He computes an average diameter of 1.1 millimeters, right? So that is his statistic, 1.1 millimeters, right? The value computed from the sample. What's the parameter? We're not given the parameter. but it would be the average diameter of the 10,000 bearings, right? The whole population. Okay, let's do another one. A 2009 survey of 218 law firms with at least 50 lawyers found that 69% of those firms had cut personnel in the previous year. Is the 69% a parameter or a statistic? Okay, two ways to approach this. First, common sense. Sometimes you do have to use common sense. Right? Do you think that 218 law firms with at least 50 lawyers is all the law firms there are with at least 50 lawyers? There's no way that's true. There are probably 218 such firms in Washington, D.C. alone. Right? There are going to be many more than that. So this survey of 218 law firms definitely collected sample data. They did not get the whole population. Right? So the 218 firms, that's a sample. Right? And so the data collected from them is sample data, and so this 69% is a statistic. Second, I can give you a rule for this one. In this course, we will consider anything that comes out of a survey or a poll to be a sample. So any data coming from a survey or a poll is sample data, and so anything computed from it will be a statistic. Right? In real life, you almost never, probably never, get every single survey back. Okay, need to say something about the two main branches of statistics. Descriptive statistics and inferential statistics. Descriptive statistics, that's the easy part. That's for describing data, like, putting it in tables or summarizing it with simple calculated numbers like the mean or the median or the standard deviation, things like that. That'll be the first, not quite a third of our course, I guess, and it's fairly easy stuff. Inferential statistics is much harder, and it has to do with making inferences. And an inference is when you draw a conclusion about a population based on the information in a sample. Right? So in our example before with the adult American males, we found the average height of the sample. I don't know, maybe it's 5'10", and we say from that, well, the average height of an American male is 5'10". Then you can ask questions like, well, how likely is it that that height is within 1 inch of the true population average? And that's the sort of thing that inferential statistics lets you express. What's the probability, say, that you're within 1 inch of the population, the true population mean, and so on. In between these two, we have to do quite a long section on probability. Right? Because although probability is not needed for descriptive statistics, it is very much needed for inferential statistics. And so we'll spend quite a long time talking about probability. First, the discrete sort of probability, where you have only a finite number of outcomes of your experiment. You've seen some of this before, like, you have an urn, a jar with 12 marbles in it, and 6 are red and 6 are blue, and you reach in and pull out 2 marbles. What's the probability they're both red? That kind of thing. And we do some slightly more complicated stuff than that, too, with probability. And then we'll move on to continuous probability, which is mostly concerned with the normal curve. That's the bell curve that you've been seeing for years. And then we'll get on to inferential statistics. And there's something about the course itself you should know here, and that is that descriptive statistics is easy. That is, there are many details to memorize. There are many little techniques to learn. but each one of them is pretty easy to learn. Right? So you should be able to do very well on the homework and any other assignments in the early part of the course with no real problem, just some work. Probability is much harder. The course becomes much more difficult at that point, and there's really not much you can do about that. It's just harder stuff to understand. And then inferential statistics is harder yet. So you're going to need to work hard throughout this course. You want to get the highest grades you can in the beginning, so that when you have difficulty with the later material, you have a kind of cushion of those higher grades. Because the later material will be difficult unless you are one of the very few. All right, just a couple more things here. An experiment, right? In statistics, this has a very broad meaning. It's really any activity with measurable outcomes or observable outcomes. Sometimes you call them that. An activity where something is happening or you're making something happen, and you can write down the outcome, the results. An outcome, the result of an experiment is actually called an outcome. You say, that if you have 5 different marbles to choose from, there are 5 possible outcomes of the experiment of choosing a marble from that group. I won't say much more about that right now, but we will see it come back many times in the course. Okay, one more thing, and that is a way to divide up data. Right? That is for analysis, to talk about it. Right? You can talk about quantitative data. Quantitative data, it's made up of numbers. Right? It's also called numerical data. Right? And those terms are used interchangeably. And this is data that comes from measuring or counting something. So it'll always be numbers. It has to arise from measuring or counting, and you can usually do arithmetic with it. It makes sense to do arithmetic on it. I'll talk about it more in just a second, that part. But the other type is called qualitative, sometimes categorical. I will use all these words, right? Quantitative, qualitative, numerical, categorical interchangeably, as everyone really does. Right? And what qualitative data is anything else. Right? If it's not quantitative, it's qualitative. Right? So examples of quantitative data would be heights, the height of American men, lengths of time, 14.2 seconds, that sort of thing. Lots of things. Examples of qualitative data would be things like eye color. Right? Eye color is going to be, you just think about what the values could be for a variable eye color, and they're going to be things like brown, blue, green, hazel, whatever, right? Not numbers. But there's a category of qualitative data that's made up of numbers or digits. Right? And it's qualitative data because it doesn't arise from measuring or counting. It's just numbers used as labels. For example, Social Security numbers. Right? Social Security numbers are numbers. You can take 2 of them and add them together or average them or whatever you like. But just because they're numbers doesn't mean they're quantitative. They didn't come from counting or measuring anything, and so they're not quantitative. And if I take 2 Social Security numbers and average them, well, first of all, I don't even have to get a Social Security number, but even if I do, it's not in any way related to the ones I started out with. It doesn't make sense to do arithmetic on those things. There are many other such examples, like International Standard Book numbers. You see those inside of, or sometimes on the back of books. There says ISBN, and then there's a number. Those are just a sign. Right? It does not make sense to do arithmetic with them, and they don't come from measuring or counting anything. All right, let's do a quick example here. learn to distinguish these a little. Qualitative or quantitative, that's the question. Diameters of eastern white pine trees. Now, what might those be? Well, it doesn't matter what the units are. Let's say they're feet. Okay, so you might have 2.7 feet or 8.3 feet or something like that. But in any case, it's going to be a measured amount of feet. You actually measure a diameter. This is going and get a number. So this is going to be quantitative. Eye color. I mentioned that before. Eye colors clearly not even made up of numbers, so those are qualitative or categorical. The numbers on the jerseys of a starting team, any team, right? Those numbers are simply assigned. They don't come from measuring or counting. So even though they're made up of numbers, this is qualitative data. All right, that's about it for Lecture 1.